Hi, my name is Aaron Dales, and for this lab we decided to observe the force of gravity and the effects of drag on gravity. So in this lab I chose one plastic poker chip and one Kleenex 3-ply tissue to drop from a certain distance above the ground and use screen capture software to measure that distance. So the first object was a poker chip. After taking video with my phone, I determined that it fell for about 7-8 frames. And throughout each frame I marked its position using the screencast software. There was a little bit of a glitch at the seconds between 2 and 3 because it seemed to be the same position, which could have just been my video capture device. It wasn't great, it was just a cell phone. So I'm going to leave that to user error, but it all turned out well in my results. I measured the distance of the poker chip, which was about 39 millimeters, and converted that into meters. And then for my second object, I chose a tissue, which took about eight steps to fall, and the tissue was about 109 millimeters. So I converted that into meters and continued the same process. Main axes, recorded it as it fell. This video was a lot smoother than the last one, and took the results and plugged them into OneNote, or sorry, not OneNote, Excel. In Excel, I made two different graphs, one of the poker chip and one of the tissue. Initially they both seemed kind of off, but that was fixed with the drag eventually. I was able to make these two charts by plugging in the data that I got from the tracker software, which was the time data, which made up the x-axis, as well as the position within the video, which made up the x-axis. So again, here are the poker chips and tissues, position versus time graphs. Here are the initial models for finding the theoretical position versus time graphs of the tissue and the poker chip. The poker chip is on the left, the tissue is on the right. Poker chip took about 0.24 seconds to fall, whereas the tissue took about 0.29 seconds to fall. So I changed the total time up here and here as well, and I kept delta t at 0.01 because it seemed like a nice rate to find the time. For the force of gravity, I made it a vector of just the ball's mass times the force of gravity, which is negative 9.1. I'm sorry, I meant to say negative 9.8. And then the ball's position would just be the ball position from that frame plus the ball's velocity times the change in time, which the ball's velocity can be found based upon the net force divided by the mass times the time plus the initial velocity. The net force divided by the mass would give you the acceleration. You know this from the equation F is equal to ma, and acceleration times the change in time would give you the ball's velocity. So here are the individual models. Oops, sorry, let's try that again. Let me just run it without the error this time. Much better. And then we repeated this process for force of gravity plus force of drag. And I had to determine for the experimental values, comparing them to the theoretical graphs, what the constant of proportionality for the drag force would be. Here are the models that came out of that process. As you can see, there was little to no force of drag on the poker chip, whereas with the tissue, there was a huge force of drag, which caused it to slow down significantly, and sorry, wrong ones. The force of drag caused it to take longer to reach the ground, which in turn caused it to have a slower velocity. Whereas the poker chip remained virtually the same, and the constant was found to be so small. Sorry. So what does it all mean? The drag model, comparing the drag model to the gravitational model for the slower object, which would be the tissue in this case, it would have a terminal velocity if given enough time, because obviously it was moving at a slower velocity to reach the ground at a longer time than it took the poker chip. And also the theoretical value for the force of gravity of the tissue versus the drag value for the tissue. One second. The experimental for the tissue initially and gravitational was reaching the ground faster, whereas we found that there was a large constant for the drag force. Because drag force was growing, or seemed to have, because the drag force was greater as over time, there would eventually be a terminal velocity for the tissue. So, what if the slower moving object was given an initial velocity? It would reach terminal velocity faster because of the forces. So this is what the model would look like if the ball was given an initial velocity. As you can see, the position versus time is pretty much linear. So it would reach a terminal velocity pretty fast if given an initial velocity. Thanks for watching. Hope you enjoyed.